There's one last part of the sun, though, that I want to talk about in more detail, and that's the photosphere. I purposely left this till the end. So let's finish this all up by taking a close-up look at the photosphere. Okay, everybody good? All right. Now, let me show you guys a close-up photograph. Sorry, I lost my train of thought there for a second. Let's get back on this train. Here we go. Here is a close-up photograph of the photosphere. We typically think of the photosphere as just being a perfect yellow circle, but it's not all one color. We get yellows, oranges, and reds, okay? And if we sorry, I'm just trying to report this over here. Okay, there we go. All right, sorry about that. Now, let's do this. Let's talk about the photosphere. Finish this up. Okay, so, sorry about that. The photosphere, what's it like? It's got yellows, oranges, and reds. What's probably different about these different regions? What's probably different about the different colors of the gas here? What's different about the yellow parts, the orange parts, and the red parts? Temperature. That is correct. It's the temperature that is different, right? And if we think of it in that terms, essentially what's happening is that the yellow parts are hotter areas and the redder parts are colder areas. And those hotter yellow regions are called granules. Granules. That's spelled Granuule. Granule. So why are there hot patches and dark patches? Well, if you remember, the photosphere is just the top of the convective zone. And if we view that kind of from the side, essentially what's happening is wherever the hot stuff is rising in the convective zone, you're going to get a granule. You're going to get one of those hotter yellow regions. And then that material will cool down, turn more orange and red, and start sinking back down. So these granules are not permanent. They're just the top of the convection, okay? But the final thing that you're going to see on the photosphere is a particular feature that we need to talk about, and that can be seen in this picture right here, okay? If we look in this picture right here, we see a bunch of spots on the sun. Here's a couple of close-ups of those spots on the sun. Does anybody know what we call these spots on the sun? What are these spots in the sun called? Good job. They're called sunspots. The spots on the sun are called the sunspots. But in particular, they're spots on the photosphere. Now, let's see if we can figure them out. They're a lot darker than the rest of the sun. So what does that tell us? What is probably true about these sunspots if they're a lot darker than the rest of the photosphere? They are colder, okay? Yeah, they're colder. So a sunspot is it's a colder part of the photosphere. Now, it's not actually cold, okay? It's not actually cold. It's just colder than the rest of the photosphere, so it's not producing as much light as the rest of the photosphere. So when you look at the sun, your eyes adjust to make this look dark. If we could block out the rest of this picture, this would actually be bright enough to blind you. It just looks black in this picture because these other parts of the sun are so incredibly bright that you can't see the sunspot next to them. It's kind of like the same problem with not being able to see the corona, Okay? Now, here we go. How do they form? It turns out that the clue as to how they formed is that they are also magnetized. They are all associated with north and south type magnetic poles, okay? Some of them have a north type magnetic part of a field and some are more south. And that tells us that it's the sun's magnetic field that's doing this. So essentially what happens is that the rotation of the sun messes with the magnetic field of the sun. Okay, and I'm going to try to do this kind of quick so we can get out of here. Normally, the magnetic field of the sun is shaped just like the planet's magnetic fields. So it pinches in at the two poles, shaped roughly like a pumpkin, right? But here's something we haven't talked about. Every part of the Earth has to rotate at one speed because our planet is mostly solid. Does every part of the sun have to rotate at the same speed? No. Why? Why can different parts of the sun rotate at different speeds? Why is that? What makes it so that that could happen? Yeah, because it's made of gas. Because it's made of gas, and that gas, the particles of the gas are not attached to each other, different parts of the sun can rotate at different speeds. All of the Earth is mostly solid, so those atoms are attached. Those molecules are attached, so they all have to spin together. But because this is gas, different parts rotate at different speeds. And it turns out that the equator of the sun, so around here, rotates a lot faster than the poles do. The poles rotate slowly, and the equator rotates quickly. And the reason that's important is that the magnetic field rotates with the surface underneath it, okay? So, in other words, if I were to, let me draw one more picture here. There we go. Let's do this. Okay, so here we go. If we were to imagine the sun's magnetic field, let's say that this is the sun. Sorry, I'm losing my steam a little bit here. We're almost done. We can imagine part of the magnetic field looking like that normally, because it's shaped like a pumpkin around the sun. But if the equator rotates faster than the poles, then that means that this part of the magnetic field will rotate faster than the stuff at the poles. So if part of the magnetic field rotates faster than the other parts, will it be able to maintain this shape over time? If part of this pumpkin rotates faster than the other parts, will it be able to maintain the pumpkin shape? No. No, it won't. So what happens is that the part of the magnetic field over the equator rotates faster than everything else, and that essentially causes this to happen. Let me show you a picture from the book. There we go. So here's a piece of the magnetic field under normal times, and here is the equator rotating faster than the poles. And that causes the magnetic field to spiral around the sun, okay? And what eventually starts to happen is that when this magnetic field spirals, it starts to get a little bit tangled. So if you look right here, they're showing little tiny tangles showing up on the magnetic field, okay? So as the magnetic field spirals because of the rotation of the sun, it causes it to eventually start to tangle a little bit. And those tangles will touch the surface of the sun, okay? They will touch the surface of the sun. And when they do, charged particles in the sun like magnetic fields. So what that means is wherever those tangles, like this little guy right here, wherever that tangle touches the sun, the gas near it is going to congregate right there, and it causes it to jiggle less. And if it jiggles less, what does that mean happens to the temperature in that spot where the tangle touched? It gets colder. That's right. So what would have formed on the surface of the sun where that little tangle touches? What do we form in that spot? Yes, that's your sunspot. Okay, so check this out. Here we go. Normally, right here, we would expect no sunspots because there's no tangles touching the surface, right? But as the magnetic field gets more and more spiraled, more and more parts of that magnetic field go into the surface of the sun, and you end up with something like this. Here's a little piece of the magnetic field, and wherever it touches the surface, you're going to get a cold spot. That's your sunspots. So as the sun continues to rotate, what would we expect to happen to the number of sunspots over time as the tangles built up? What would we expect to happen to the number of sunspots? We would expect them to happen more and more and more over time. But let me show you a quick graph from your book. This right here, we've been tracking the number of sunspots on the sun for literally hundreds of years. Back before the camera was invented, we were counting sunspots on the sun. So a lot of scientists went blind for this data right here. And this right here is the last 100 years. It's the number of sunspots every year. And does it just keep increasing over time? No. What happens over time? We increase and then we decrease. Every 11 years, we increase and then we decrease. We increase and then we decrease. So there's a cycle here called the sunspot cycle that's 11 years long. And essentially, in the first half of the cycle, the sunspots build up like we were talking about before. So eventually, though, the sunspots need to disappear in the second half of the cycle. So what happens? Well, it's actually pretty simple here. If we go back to this picture, imagine like this was a basketball, and these were some rubber bands, and you spiraled them tighter and tighter and tighter onto your basketball, giving you some sunspots. What will eventually happen to these rubber bands if you keep wrapping it tighter and tighter and tighter? What will eventually happen? It'll break. That's correct. It'll break. Essentially the same thing happens here. If the magnetic field wraps too tight, just like a rubber band, it will eventually snap, okay? It will eventually snap. And what happens is that those tangles break too. But if the tangles were making the sunspots and we break the magnetic field that was making the sunspots, that means the sunspots will start to go away. So essentially, the reason there's a cycle is that at the beginning of the cycle, there's no sunspots. Then as it wraps tighter, it makes tangles that make sunspots. But if you wrap it too tight, you break your tangles, and then the sunspots go away, okay? And then at the very end of the cycle, the broken magnetic field reforms back into a simple pumpkin shape again to just completely restart the cycle over and over and over again, okay? Now, somebody's asking a question here. I'm going to answer that question as the last thing that I'm going to be talking about here, and this is important because it turns out that these tangles don't just make sunspots. They also make something else, okay? Remember, I said that the charged particles of the sun like the magnetic field, and so they kind of congregate right here, and that causes them to slow down in this region. And so it'll be cold right here, relatively. But if charged particles like that magnetic field, and that magnetic field is starting inside the sun and goes out of the sun, what is some of the material of the sun going to want to do right here? What's some of the material of the sun going to do in this region? Yeah, it's going to escape the sun. It wants to follow that magnetic field. So while some of the gas congregates right here and cools down, some of the other deeper, hotter gas of the sun will actually burst through that region fast enough that it's not going to heat up the sunspot, but you'll get material bursting out of the sun here. And that is called a solar flare. Let me show you some pictures of some of these in action. Here's a couple of small solar flares. I showed you this picture before, but this right here, this is a solar flare. And you can actually see exactly where the magnetic field of the sun is as this material is launched above the chromosphere and falls back down towards the sun. If it goes out fast enough, it can burst straight into space, okay? And just to give you an idea, like here's another solar flare happening. These things are amazing. If I were to kind of put my finger out here, the tip of my finger is about the size of Earth, okay? The tip of my finger is about the size of Earth in this picture. So that's a lot of hot gas bursting through, okay? Here's an even bigger one. So here again is hot gas bursting out of the sun, riding that magnetic field, okay? And that means that there's not always the same amount of solar flares happening. And we can look at the sun and tell if there's going to be a lot of solar flares happening. When are there going to be a lot of solar flares? How can you look at the sun and know there's a bunch of solar flares going to be happening? What would tell you? What would tell you a bunch of solar flares are going to happen right now? Yes, it's the number of sunspots. Remember, the tangles in the magnetic field are what cause both the solar flares and the sunspots. So if you look at the sun and there's a bunch of sunspots on it, that means there's probably going to be a lot of solar flares too. And if you look at the sun at the beginning of the cycle when there's no sunspots, there's also going to be very, very few solar flares, okay? Right now, we are closer to a minimum than a maximum, I believe. So we don't actually have too much of this kind of activity. I mean, it's happening enough, but we're not at a maximum right now. So we're not having the whole ton of this happening. When this stuff shoots out of the sun, do we need to worry about this? Is this going to kill us? Is this going to kill us when it comes and hits the Earth? No. We're going to be fine. What protects, and it's good, something protects us. If there was no protection from this, this would have happened every 11 years. So we would have a chance of this coming and hitting the Earth every 11 years. Clearly, that's happened in your lifetime and we haven't all died. What's protecting us? It's the magnetic field. It's the magnetic field. Yes. Remember, the reason this stuff is able to come out of the sun is it's riding the sun's magnetic field. So when it gets to our magnetic field, it wants to turn and follow our magnetic field as well. It may push in on the magnetic field a little bit, enough to interfere with satellites, but it's probably not going to get all the way down to the surface of the Earth, okay? What it would do is it would make the auroras look a lot cooler when it was happening, because a lot more material would be making it to the poles to light up the poles than usual, okay? Yeah.